Today we're going to talk about async I/O, and I'm going to share with you a couple of details of how to actually make use of async I/O, especially if you're using it along with a web server like Starlet or a tool like Fast API. And in order to do that, why don't I first share my screen with you? And we'll get started with our very first question. What is a coroutine? Well, here's the bad news. Nothing in Python is what it's called. And this ends up getting really, really frustrating every time we talk about async I/O because between you and me, well, if we look at something that looks like this, we'll say, okay, that's a function. I guess that is a function. That is what it's called. But if we look at something that looks like this with a yield in it, you and I would call that a generator. But that's not a generator. Python says, no, that's not a generator. That's a function. The thing that you get when you invoke this, that's a generator. And you and I would say, well, hold on a second. No. That's a generator versus a generator instance in that distinction. But the CPython interpreter itself makes no mention at all of generator instances. There's just a function which returns a generator. And what the CPython interpreter calls a generator is what we would call a generator instance. So we're already confused. Now, if we happen to have a generator and to the left-hand side of that yield, we are saving the result of the yield expression, you and I wouldn't call that a generator. You and I would call that a coroutine. But the Python interpreter and the documentation as it stands today says, no. That's just a generator with a send operation. So here we can do a next, and then we can send something into this. And of course, here we'd have to put this into a while true maybe, just so we can do this without getting the stop iteration. And so we have this other terminology. But let's talk a little bit about why we might call this a coroutine in the first place, why it is that we call these things which nobody else in the Python interpreter calls them. Well, it turns out when we're talking about a function, what we're usually talking about is we're talking about some computation. And that computation may have multiple parts to it. For example, that computation may do three things. It may take some value and add something to it. It may take some value and multiply it. It may take some value, and it might raise it to a power. And if we wanted to return all three of these, well, we would take the data in, we would return something, and there we go. We have our function. What we can think is the function is some computation, and in some ways we could break that computation down into parts. Here, we can't really do anything with those parts because if you think about it, maybe I could do something with the +1 before I go and compute the ×2 or the raised to the third power. These might be slow operations, but there's really not much I can do. I can just invoke this thing, get the result, and return. But if I were to model this as a generator, what I'm really doing behind the scenes is I'm saying, this computation actually consists of three separate parts. The computation of the +1, the computation of the ×2, and the computation of raising to the third power. And as a consequence of modeling this exact same computation, just very slightly differently, I get the ability to do something with this structuring that I've added. Specifically, I can run these pieces independently. Let's put in some data here. And I can go and I can do some work in between. So I can say, I don't need the raise to the third power in order to do something with the first computational result. I can get that first computational result and then go do something else and then come back and do something with the second computational result and do something with the third computational result. Now, code like this probably doesn't really exist in the real world because you can think that somebody looking at this line of code here is like, wait, is that the ×2 or the raise to the third power? They wouldn't be able to tell from just that next. And so likely what we would end up seeing is some computation that maybe can be broken down into parts because it's running on some large data set, and each part of that computation is one incremental part of that. For example, each pass through that loop where the different passes of that loop may be indistinguishable from each other, but each pass of that loop may be one part of this. And so here, we can do something like run this computation on a very, very, very large data set, something that if we tried to do this to completion would never return because this is just way too much data. I don't have that many seconds in my life to wait for this, but I can do something like grab just the first part of this computation, or maybe making use of something like the itertools module, I might slice out just the parts of the computation that I care about, for example, the first 10 steps. And let's just make sure that we spell everything correctly. And there we go. I slice. And here, of course, we don't want the next. And so there we go. And so we could never run this computation to completion. We simply do not have that much time or that much memory. But as a consequence of this structuring, we can run this partially. Effectively, what we call a generator, that isn't really a generator, but what we call a generator is really just the idea of taking a computation, breaking it down into parts, and then doing something with that structuring that we've added. Well, if we think about this, a function is really the idea of you get data in, you go and you do some work, and you send some data out. And the idea of a generator is, oh, this work has parts associated with it. So we have work step 1 and the corresponding output. And we have work step 2 and work step 3 and their corresponding outputs as well. We've done some generalization of this idea of a computation. We've broken it into parts. And that's really the general idea we think of when we think about a generator. Well, if we use a little bit of outdated terminology to refer to this entity, and instead of calling it a function, we call this a subroutine, then the terminology for coroutine might be a little bit easier for us to understand or to at least appreciate. In essence, if the generator is this generalization of a subroutine, instead of having one input and one output, but you have one input with the work broken into parts and each incremental output, a coroutine is just the exact same idea, except you can pass it new input. You can give it some portion of input and do some portion of work and get some portion of the output, some portion of additional input, some portion of work, and some additional output. And in Python, we really don't distinguish, mechanically at least, the generator from the coroutine. But you can see at least why we choose that formulation, or at least that terminology. Well, it turns out that this thing here is not a coroutine, at least according to the documentation, or at least according to the interpreter. And these days, when we talk about coroutines, we're often talking about things that look like this. But actually, this is also not a coroutine. And not just in the sense that it's an asynchronous task. This is also a function. The thing that you get when you call it is the coroutine. And you have to do a little bit more work on this thing in order to actually get anything useful out of it. You have to put it into a scheduler. Here's the general idea behind all of the async IO stuff and why it is that it evolved out of what we historically called generators, what we historically called coroutines. The names are all over the place, but this is why it is the way that it is. In general, if we had some process that could be broken down into parts, for example, an infinite loop that just prints out, I don't know, the name of some task that we're running. And we give this thing a name, and we'll call this a task. And we say, here's task AAA, and here's task BBB. This code will never run, because this loop is infinite. And the loop doesn't have to be infinite. It could be just very, very large. This code will never run. Well, if this code is doing something that requires some time that we spend going off and waiting for something, for example, this code maybe opens a file, or it makes a network request, or it calls a system call. If it does some work that doesn't require computation, just requires waiting for a result to come back, we're wasting a lot of time here, even if this isn't an infinite loop. We're just waiting for some result to get back to us, and all of that time that we're waiting, we're really not doing anything with our program. So it would be advantageous if we could recapture that time, and if we could do some kind of interleaving where these two units of computation are able to cooperatively decide, oh, you do one unit of work, I do one unit of work, you do one unit of work, I do one unit of work. And in fact, all that's required in order to make this work is for us to denote, oh, where is one unit of work? Well, the yield is how we denote one portion of a computation. And now what we get is two computations that are truly infinite in the total size of what they do. But as a consequence of the structuring, well, we can do something with this. We could put this into, say, a scheduler. And we could say loop forever for each task you have. Just do the next step of that task. And we could schedule these two units of computation like that. And of course, here we need to make this like that. And here, let's put in a sleep just so this doesn't span our screen. There we go. And there you go. We have some interleaving. And if we were to then take this general idea and build it down further and further and further from the Python level into the level that adapts our C code into Python down into the C level and further, and we're to get this all the way through our framework, what we could say is, you know what? In addition to allowing these 2 units of computation to interleave, when one unit of computation is off doing something that's just going to revolve around waiting, a system call, opening a file, making a network connection, whatever the case is, I'll maybe put an implicit yield type operation there. I'll make it so that I can denote that, you know what, I'm waiting. Somebody else can do some work. Well, this scheduler is not a very good scheduler. It's a round-robin scheduler. If one of these units of computation takes a very long time and the other unit of computation takes very little amount of time, they still get an even number of steps that they can run, so there's no time slicing. But you can imagine that if we took this general idea and we expanded this to add in fairness of schedulers, we added support to this all the way down into the deepest levels of our stack, well, we'd come up with something that looks very similar to asyncio in Python. The whole idea of asyncio in Python is as follows. We're going to use some mechanisms that add structuring to a computation. Those mechanisms, historically, were just piggybacking off of the things that we would call generators. However, as a consequence of wanting to make a clean break from what we call generators to this new mechanism, and as a consequence of wanting to support the idea of generators even within this idea of scheduled code, well, we're going to add in some new syntax. And so this is probably the simplest example that shows us the idea of asyncio without ever using asyncio. Here's the exact same example, but actually using asyncio. So we'll just import a couple of things here. We'll have a run and a gather. We'll make this an asynchronous task. Instead of a yield, we'll make this an await. We'll actually await the sleeping of, let's do 1/10 of a second here. We don't need to write the scheduler that's already been written for us, and that's sitting behind the scenes, but we do need an entry point like that here, and we'll gather our tasks. And there we go. And we'll have to actually enter that entry point. Basically, the idea here is we can model individual computations as some kind of structured units. We can take an event loop that somebody else has written that ensures that if we have multiple computations that can be broken down into parts, we can run one part here, then one part here, then one part here, then one part here. We can take support built into the language all the way down to the deepest levels to say, oh, and also when something behind the scenes happens, like a sleep operation or a system call type operation, we can release control back to that event loop. And we'll do that explicitly. We'll talk about that in a moment. We'll do that explicitly and bring all of these pieces together to allow us to recapture time that would otherwise be lost in our program waiting for something to give us another concurrency mechanism. Now, I told you I wouldn't talk too much about multiprocessing or threading, but I do want to draw a strong contrast to those approaches, focusing primarily on what asyncio gives us. If we think about all of the approaches that we have when it comes to any sort of concurrent programming, well, multiprocessing is one, threading is another, and asyncio is another. When we think about multiprocessing, what we're talking about is multiple separate Python interpreters. As a consequence of being separated, they don't necessarily have to sit on the same machine, although the way that multiprocessing communicates between the processes is by sending pickled data between these processes, so they probably actually, if you're using the multiprocessing module, sit on the same machine. But as a consequence of being in completely separated process spaces, they don't share any memory, and they don't share any other resources. So we don't have any confusing, oh, did this thing over here touch the data and this thing over here was going to read from it? Did this read happen during this write? We have none of that confusion with multiprocessing. And we're able to use the entirety of the computational resources that our machine has. We can allow our operating system to say, put this process on this thread, or sorry, on this hyperthread, or on this core, put this process on this CPU or on this core, and max out the the cores that are in our machine. Unfortunately, it makes it a little bit tricky for us to share data. Because these are separate processes, we have to rely on pickling to move data around. And so anything that's extremely stateful cannot be moved between these processes. So you can think that's actually quite a few things. You can't move, for example, an open file handle between the processes. You can't move an open database handle. Anything that has hidden state that'll be hidden in the deeper layers of your interpreter cannot be shared amongst these processes because they're fundamentally different, separate processes with their own memory. When we talk about threading, we're talking about one single process, one single interpreter. And we're talking about the operating system coming in behind the scenes and deciding, oh, this thread over here gets to run. Okay, no, that thread no longer gets to run. This thread over here gets to run. So we're talking about one single process. We're talking about an ability for things to be shared much more readily and for us to share very rich stateful things among the units of computation. However, the scheduling is preemptive. And what that means is, well, we don't really know when each unit of computation is going to run or not. It could run in a fair way. It could run in an unfair way. It's the operating system who's really deciding. And as a consequence of some of the limitations of what the operating system can see, we have historical constraints like the global interpreter lock. But even beyond that, we can't look at a line of code and say, this line of code is guaranteed to run before this line of code. These two lines of code are guaranteed to run with nothing coming in between without explicitly having to add locks. When we talk about async I/O, we're talking about one single process, but the scheduling is cooperative. What that means is, instead of looking at that code and saying any line of code could run at any time depending on a scheduler who we're giving no information to and has no information about what our program does, we explicitly cooperate and say, I'm ready for somebody else to do work as of this point in the code. And the way that you indicate that is via that await keyword, via that program structuring that the generators first introduced into Python. As a consequence, we do not have this head-scratching, wait, these two lines of code, do they run with nothing coming in between? Is this thing going to set something, but over here this thing's going to read, and they're going to race to try and figure out, are you setting the most recent value? Are you reading the most recent value? None of that exists in async I/O. Async I/O gives us the ability to recapture a lot of time that we spend waiting for something in our programs without having to scratch our heads trying to figure out what on earth is going on when these different units of computation are running simultaneously, which is running when, do I have to put locks here or whatnot. Tends to be a much easier way for us to analyze how our program works. However, if you think about it, async I/O cannot speed up a computationally bound program because you have one thread, one process, and they're all making use of that one same interpreter. So if you have multiple async I/O tasks, they're doing computationally heavy work, well, they're just going to be serialized. Threading historically also has the same limitation as a consequence of the global interpreter lock. Although even if we remove the global interpreter lock, there is a material difference between threading and async I/O in that the scheduling is preemptive. Multiprocessing doesn't have that limitation at all because you have separate processes and they can just do whatever they want, and you have to be very explicit about how you share memory. So you can see that these approaches form something of a spectrum. The whole idea of coroutines when it comes to async I/O is this is our way to take some computation, to break it down into parts, and to indicate this at this point in the computation, I'm allowing anybody to go do any additional work. And we have an additional syntax and some additional mechanisms, additional data model methods to support this, together with some additional complexity, as we'll discuss. Now, to draw this to a conclusion, I want to draw your attention to one or two key points. First, nothing is what we call it. And I know this is very, very confusing. It confuses me every time I have a conversation with somebody and I say, no, not that coroutine, this other coroutine. But fundamentally, the core of the idea behind all of this is a generator or a coroutine is a structured computation. If you can put some structuring behind a computation, well, what can you do with it? Well, what you can do is you can schedule the parts of the computation. And this requires deep-seated support in your interpreter. It requires an event loop that somebody's written, and it requires a scheduling. This idea of scheduling is very important. We're going to see when we talk about blocking and how you can implicitly block. what happens when, we don't really get a good sense of what it means for code to be scheduling aware or scheduling ignorant. But I want to move on, and I want to talk about a lot of the mechanics behind async IO in Python.